Hello, and welcome to today's WJE webinar. My name is Liz Pimper, and I'll be your moderator for this webinar, Protecting Your Glass Assets, How to Approach Damage and Breakage. During the next hour, WJE glass expert Mark Schmidt and Michigan Tech assistant professor and glass researcher Dr. Stephen Morse will discuss a variety of glass conditions, some of which require repair or replacement. They will cover relevant case studies to illustrate the efficacy of repair versus replacement for various conditions, and will also address the timely topic of tempered glass breakage and heat soak testing. This presentation is copyrighted by Wiss, Janney, Elsner & Associates. And now I will turn it over to Mark Schmidt to get us started. Mark?
Thank you, Liz. Good afternoon, good morning, depending on what time zone you're in. I'd just like to mention that this topic has captivated my attention for a couple of decades now. And I know that Stephen shares my passion for this topic, having obtained his PhD in glass research and continues to be one of the foremost glass researchers in the United States. It's also very encouraging that over 200 of you have registered for this webinar today from approximately 150 different institutions. So Liz already touched on some of these learning objectives in terms of looking at different types of glass damage. We'll explain why that's in quotes later. We're going to distinguish between what's acceptable and not acceptable, compare different techniques for remediating glass surface damage, then lastly touch on a timely topic of spontaneous glass breakage. And here's a brief outline of how we're going to do that. Before we move into that, I'd like to coin a term that I hope sticks with you through the balance of this presentation and beyond, and that word is glassets. Cleverly embedded in there is glass and assets, and we'll talk about why they have become such a significant factor in the exterior building envelope. We'll take a look at some common causes of glass damage, including the curious believe it or not category there at the bottom. I will continue with a discussion of how we determine whether, quote, damage is really something that's not allowed by current standards, and look at the options for remediating that kind of surface damage. Then I'm going to hand it over to Stephen, who will take a deeper dive, technically that is, into the structural implications of remediating glass surface damage and give an example of some costs using a case history. And then he will again turn it over to me, kind of an unrelated but timely topic of spontaneous glass breakage. So let's take a look at why glassets are so important. This is a nice looking building in Hong Kong. Not terribly ornamental, doesn't have a lot of jewelry, but the exterior building envelope probably ranges anywhere from 15 to 25, maybe even higher % of the total building cost. And what's more is the costly glass within the building facade can make up about 50% of the overall building envelope costs. And the reason for that is a couple of bullet points here. There's a variety of coatings, frits, laminates, gas filling, blast resistance that can drive up the cost. Then because of the wide variety of glass products used on buildings nowadays, there's typically limited or no attic stock at the completion of the building from which to draw on to replace any of those products. They become harder to match. There's much longer lead times, especially if that glass is internationally sourced. And then with structural silicone glazing, the removal and replacement of those glass products becomes expensive as well. There may be some adjacent high-end finishings and furnishings on the interior. So you can see that your glass sets can quickly become a liability. It's not unusual to have single unit replacements cost upwards of $10,000, when the product is unique and the access is difficult. And that's not to mention any replacement, any costs related to loss of business and relocation, et cetera. So before we get too far into it, let's just talk about a little bit of terminology for now. On the left, you can see what we call a double glazed insulating glass unit. On the right is a triple glazed insulating glass unit. All our examples today will probably focus on the double glazed insulating glass unit, and the individual panes of glass are what the industry terms lights. And that is the proper industry term and spelling for that, for the individual glass panes. So now let's take a look at the variety of ways that glass can become blemished. And I'm using the word blemished because technically it doesn't become damage unless it's not allowed by current standards. So you can see in this photo that there's some fine spots that might otherwise be benign, except they're just opposed against that costly fine dotted frit pattern there that makes it easier to see. And the question might be, how do we get that kind of damage or pit marks in the glass? Well, we can tell you that chop saws and glass do not play nicely together. The chop saw ends up broadcasting hot, burning metallic components against the glass that's close by and burns itself right into the surface. Then you might think that construction cleanup would do nothing but enhance the appearance of the glass rather than detract from it. Well, it all depends on what you're trying to remove from the glass and what you're trying to use to remove it from the glass. Now we're zoomed in considerably on the two right-hand photos, so you might think that those scratches are kind of benign, but I'll leave it to your discretion as to whether you would consider these type of scratching in these photographs benign or egregious or objectionable. They're certainly numerous and closely spaced. And by studying them closely, it can be helpful in identifying the cause of the surface blemishes. Then you might wonder what kind of blemishes can arise from just normal operations. Well, for buildings such as this that have cementitious components on the exterior facade, whether it be exposed concrete, precast, brick masonry, mortar, etc., they can leach what we call alkalis onto the glass surface, and those either just sit on top of the glass surface as tenacious stains, or they can actually embed themselves and etch themselves into the glass surface. So in the process of trying to remove these type of stains, we've encountered buildings like this in the past where a proprietary glass cleaning compound was used and resulted in an unwanted artistic effect, as you can see. And many of those scratches are barely perceptible except under direct reflected sunlight, so it can be tricky to pick those up. Another category of blemishes and causes of blemishes are natural disasters. Here you can see the recent path of Hurricane Dorian that undoubtedly had packed some sufficiently high winds to pick up debris in the wind stream and broadcast it against the sides of many buildings. So that's the common denominator in these natural disasters. On the right here, you can see tornado in the upper right-hand photograph. Still pretty common. Less common, but still happens frequently, are microbursts shown in the bottom right-hand corner. And again, they all have similar characteristics in terms of blemishes that we'll take a look at shortly. Here you can see a building that sustained a lot of damage to the exterior facade as a result of the 2008 tornadoes that ripped through downtown Atlanta. Here's another view looking out from a building that we were involved with, showing the large number of surface blemishes that have been highlighted in dry erase markers. So you can see how prolific the damage can be too, depending on the winds and the amount of debris in the wind stream. Believe it or not, many tenants and office buildings will be surprised once you start highlighting this damage. It kind of points to the fact that tenants might be somewhat oblivious. Condo owners probably pay a lot more attention to the $1 million windows that they paid for. Here's another building. This happens to be in downtown Miami when a pretty wimpy Hurricane Wilma came waltzing down Brickell Avenue in about 2005. So in case you can't tell, here's a close-up of the facade. There's a lot of broken glass, a lot of board ups. This particular building was downstream of a hotel that lost a lot of glass during that wimpy hurricane, and it ended up being broadcast against the side of the building. And the common type of surface blemishes that result from these natural disasters are what we might term rubs. In the upper right-hand corner there, it just kind of looks like a skid mark against the surface of the glass. Or what we call impact points, or impact or point blemishes. And you can see that, that there can be a large number of those in a small area from these type of events. In the course of repairing building facades, we've seen glass become blemished. These type of blemishes are kind of a close cousin to some of the others that we've seen. But here's a variety of tools that are sometimes used in the process of these facade restoration projects to scrape debris off the glass. First, you have just a common safety razor on the left, and then a wider blade, probably 6 inches wide on the right, both razor blades. They can be benign if they're used in a controlled fashion and are not run in a back and forth motion. And care is taken when you're using those on heat treated glass. That would be heat strengthened or tempered glass. Then less common, but still found routinely in workers' toolboxes would be a 5-in-1 tool or a flat bar, which we've seen used to try to remove debris from glass. And then our favorite would be the tile scraper. And yes, that device is typically used to scrape your old 1960s, 70s linoleum tile off your floor when you're remodeling your kitchen, for instance. So we've seen that used to remove cementitious debris from glass. So particularly when it's run in a back and forth motion, when the blade is rusty, as shown in this photograph, and that was the exact tool pulled out of the toolbox of the workers close by, you get these type of deep, somewhat prominent scratches, not surprisingly. So under the much anticipated category of believe it or not, I'll pose the question as to whether or not this beautiful nighttime sky with fireworks looks remotely like this surface blemish. And you may have guessed it, but this occurred following an NFL football game when a pretty excited fan, perhaps inebriated, detonated some fireworks adjacent to a significant building. And this kind of surface debris was found all the way up to the 16th floor of the building, creating many prominent pits and marks, as such as shown in this photograph. So now that we've looked at ways we can blemish glass, how do we determine whether those blemishes are in fact damage? And there's really only one standard in the US that's used to determine acceptable surface condition of glass, and that's ASTM C1036, entitled Standard Specification for Flat Glass. So we'll take a look at some of the criteria there, but the premise of this standard is you begin observing the glass from prescribed viewing distance, starting from the furthest viewing distance from the glass and moving progressively closer, so that the viewer is not biased. We believe there should be another assistant at the glass marking whatever blemish is that the observer sees and determining whether it's a blemish or maybe it's just some benign surface debris that can easily be wiped off the glass. So once those blemishes are all marked, the next step would be to measure their size, as we're doing in the upper right-hand photo, as well as their spacing, shown in the little cartoon there on the left-hand side. And because we want to get an idea about the likelihood of being able to restore this glass without replacing it, we will also go ahead and measure the depth of those blemishes using a needlepoint digital micrometer as shown in the bottom right-hand photo. So once that's been done, we go back into the standard, and there's a couple of tables in the standard that are helpful. One is what they call point blemishes, and these would be for impact points typically. And the typical quality of glass that's used on virtually all architectural glass projects is Q3 quality. What we'd like to point out from this table is that if you look over in the left-hand column, for blemishes just slightly less than 0.05 of an inch, they are allowed in any quality on the glass from the prescribed viewing distance of about 3 feet. So if they're small enough, they're allowed in any quantity. Another thing we'd like to point out is this table is specifically set up for 1/4 inch glass. If the glass is thicker, then there can be a greater, proportionally larger blemishes allowed for the same conditions. So that's something to be aware of. The second table lists allowable values for linear blemishes. So these would be scratches. Again, we'd like to point out that for the light intensity viewing distance, so this would be something that you can first observe very close to the glass, like 8 inches away from the glass. But if that's the first time you can observe these blemishes, you can have scratches up to 3 inches long at that point, and they're still allowed. So this is all to point out the fact that glass is not manufactured, transported, or installed in such a manner that it's going to end up on your building facade in a pristine condition. There may, in fact, be relatively large blemishes that are allowed that may predate any event, any significant event like a natural disaster. So that's important to realize as well. Well, now that we've identified what constitutes damage, what are our options in terms of remediating that damage? Well, there's 3. One is to replace the glass product. The second is to use some of the proprietary glass cleaning compounds available on the market. And lastly is to perform a more labor-intensive polishing effort that finishes with a cerium oxide paste that restores the glass to optical clarity, and we'll take a look at that shortly. As we already talked about, replacing the glass can be very costly. There are your glass sets, and they've come to cost a lot of money. Secondly, we have seen glass cleaning compounds, one of which was highlighted in a previous slide, that contained either silica or hydrofluoric acid that has done more damage than good when it's been used on the sides of building facades. So we would recommend, and it's also endorsed by many of the major glass manufacturers and fabricators, for removing surface blemishes is to use the last approach. And what does that look like specifically? Well, initially, you mount some sanding discs of different grit size on the end of a polisher, and you try to polish out and get to the bottom of the blemish, completely remove the blemish. And you can see that that makes the glass cloudy. But you use progressively finer and finer grits of sanding discs to restore the glass, to actually to feather out the repair area so you minimize any distortion. And in this process, you might get concerned that you're heating the glass to high temperatures, and specifically if it's heat-treated glass to begin with. However, in measuring those temperatures using infrared camera, we've seldom found temperatures rising above about 300 degrees, which is relatively benign for the glass. But let's take a look at a typical cleaning process here. And you can see that the worker is starting with a relatively coarse grit sanding disc to try to get to the bottom of a marked blemish. And then he's mounting progressively finer sanding discs on the end of the polisher. He's feathering the repair area out to minimize any distortion. And then he's going to begin the final process of restoring the glass to optical clarity with the cerium oxide solution and paste. So you can see it, he's doing quite a neat job here, but it can get messy at times. And there's several iterations required with this polish because you have to use it in a wet condition. You don't want it to particularly dry on the glass surface because it is a very fine abrasive, but yet it doesn't result in any significant glass blemishes or scratches. So he's going to check whether he got to the bottom of that. It looks like he's not quite satisfied. There's probably some cloudiness left on the surface of the glass. So one more iteration with the cerium oxide polish, and now he's content that he's gotten to the bottom of that scratch. So as you can see, it's a pretty labor-intensive process. There's another alternative, and that involves using some automated equipment that we'll show in this video, which recirculates that cerium oxide slurry through this equipment. It's all recirculated under that rubber shroud that's being pushed across the surface of the glass. And the only thing being broadcast against the surface of the glass is water, and that helps to lubricate in front of the device, making it easier to push along the surface of the glass. So this process can be significantly neater and better suited, especially for widespread polishing applications. So, looks like he's finishing up with that process. So let's take a look at what kind of results you can expect. This particular project that I showed earlier with the artistic scratches that were induced by a proprietary polishing compound or glass cleaning compound. This isn't the final product, but you can see highlighted in the orange areas where this automated process was initially used as a first pass to improve the appearance of the glass. And you can see it was dramatic. Subsequent passes restored the glass to acceptable optical clarity. So you can see that there's a considerable improvement in this process. Now, as advertised, we're going to take a hard turn here, or a turn toward the analytical side of things, and I'll hand it off to Stephen, who will talk about the structural implications of polishing the glass, particularly heat-treated glass.
Thank you, Mark. So I'm going to go through a brief overview of how we calculate the load resistance of window glass using the contemporary standard in the United States. And then I'm going to go on to discuss how does glass polishing affect heat-treated glass. And then I'm going to share a case study with you after that, and we'll talk about what we find from the case study through this process. So first I want to go through and talk about what is that standard. And so in the United States, our primary standard for determining window glass strength design, our load resistance as we like to call it, is ASTM E1300. And this standard has been in effect in use for the past 30 years or so. And its most recent iteration or addition has been in 2016. And of interest to us for today is this addition of the analytical procedure that was added in this last edition, which provides us a probabilistic method to calculate the window glass load resistance. And it incorporates or takes into account the window geometry, so that's including the thickness of the glass, the rectangular dimensions of the glass, and also the construction. In this case, we're going to be talking about some double IG units or insulating glass units, the heat treatment of the glass for a desired specified design load, both magnitude and duration. So what is heat-treated glass to begin with? Well, heat-treated glass starts with annealed glass, and so for our purposes, this is just going to be regular float glass that we cut, and then we run through an oven and we heat it up to near a melting point, and then we quickly cool it or quench it, as the industry term is, imparting a residual compressive surface stress. And we kind of represent those by these kind of blue gradients on the top and bottom surface of the glass. Now, this RCSS is measurable using various optical devices that are available on the market. And if we zoom in on our graph a little bit here, we can see that this device will provide the residual stress through the surface of, or through the depth of the thickness of the glass. And at the top we have, the left side we have the compression zones. Those are on our two surfaces as we expect. And on the right side we have the tension zone at the interior of the thickness. Now we distinguish our different types of heat-treated glass as either heat strengthened or fully tempered. And that distinction is based on the magnitude of the RCSS. So being able to measure it is important as we go forward. All right, so the analytical method relies on this kind of nasty looking set of equations that we have here. And I'm not going to go into too much detail with this. But these equations, in conjunction with numerical stress analysis, something like finite element analysis, which you're probably familiar with, we are able to calculate a probability of breakage based on the loading conditions and the glass geometry. So in this case, the output from our numerical analysis gets used in these equations with these variables. So that's the maximum principal stresses and the associated tributary area of those. And you can also see that the RCSS is taken into account here. And the basic idea is that in order for the glass to fail, we have to put that surface in tension. Thus, we have to create a stress in the glass that overcomes that residual compressive surface stress that is imparted by the heating and quenching process. And this is actually why heat-treated glass has greater load resistance. For our design purposes, RCSS is taken as the minimum values that are defined in C1048. But for our purposes, or for forensic purposes, we can use the values that we actually measure on the glass because we have the actual glass to measure. So we'll get rid of that. To kind of go through an illustration of how this works, we would start with our desired glass geometry. So this would be the thickness as well as the rectangular dimensions of the glass. And if heat treated, we would need the RCSS as well. Then we would perform that numerical analysis. And so we have those nice rainbow pictures that you're probably familiar with. And then we're going to go on and calculate that probability of breakage using those nasty looking equations we saw previously. And this can be done either simply in a spreadsheet from the output of our numerical analysis, or there's various custom software available on the market that will also do this. Once we have that, then we check this criterion that's built in the standard of 8 in 1,000. And so if our probability of breakage comes out to be less than or equal to 8 in 1,000, then we're good to go for our design load. If it's greater than 8 in 1,000, then the design does not work and we have to make some sort of change. So this limit's going to become important to us when we look at our test cases here in a minute. All right, so what are the implications of polishing heat-treated glass? So as we mentioned, we have a blemish, as shown here, and when I polish the glass, we're actually removing glass material. Okay, so at the point of polish, we have actually a zone of thinner glass thickness compared to the original glass thickness. And in addition to that, we removed reduced some of the residual compressive surface stress as well, because that was part of the thickness. So the question is, well, when we actually polish real glass, how much thickness are we actually removing? And what is the corresponding reduction in the RCSS? And because that's going to lead us to how much does the load resistance or the capacity of our window reduce consequently from this polishing? So to that end, we're going to explore a case study. And what we have here on the left is Mark using one of the devices that's available in the industry to measure the RCSS in glass. And it is principally driven by a computer with a specialized software program. And among other things, when you measure, you actually see that profile. We've seen kind of some of those graphs previously. That's from this device. And what Mark and I wanted to do before we started some of these case studies was to come up with a kind of a theoretical or rational method that we thought would be a reasonable way to approach as we reduce the thickness, how much is that RCSS going to reduce with it. And so we wanted to kind of compare that method, because if we had a method that worked reasonably well, then we wouldn't necessarily have to measure the glass every single time. So just let me orient you to this particular graph. Along the x-axis, over on the far left, this is the original thickness, and as we move to the left, we're reducing the thickness during polishing. It's just a ratio, polished over original. And on the y-axis, we have the corresponding measured RCSS. So at the top was the original RCSS, and then we see that ratio of RCSS reducing as we go down. So I said we wanted to compare it. So for the case study that we're talking about today, you can see that we had quite a few different measuring points, some above and some below, most of them below. And so when we kind of fit a trend line to that, we see in general that what we measured was lower than what we predicted. So this indicated two things to us. One, our rational methods didn't work very well in this particular case. So we could surmise that that may not be the best way to predict what's going on in the future for other projects. And two, it really drives home the point that we really need to measure and check these on a case-by-case basis. So in our case study, we polished and checked several units, and the max thickness reduction that we found was 0.008 inches. That's in no way related to the 8 in 1,000 limit that we talked about earlier. It just kind of coincidentally happened to have the same number. And a maximum RCSS reduction of about 28%. Now remember, we're polishing, as we saw in our videos previously, some localized area. So the vast majority of the glass is still as it was originally, thus not reduced in any way. However, to simplify our analysis to check the load resistance and to add just a bit of conservatism, we're going to go ahead and analyze our capacity based on the reduced thickness across the entire plate and the reduced RCSS across the entire plate as well. Okay, even though we know that there was only one location where that actually was polished, or one or just a few locations, we'll say, potentially. So in our case study, we were looking at, in this case, 4 different sizes of glass with 4 different constructions. So let me orient you to these. So these were, we had 2 that had 1/2-inch heat strengthened laminated glass on the exterior, had a 1/2-inch airspace, and then we had a 1/4-inch fully tempered piece of glass, monolithic, on the inside. So this was floor to ceiling. Fully tempered was there for required building codes. On the second 2, different location, different scenario, we had 1/4-inch heat strengthened on the outside, a little bit different thickness, 7/32 or 27/32 for the airspace, and we had the same 1/4-inch on the interior. So what we polished in this one was that interior 1/4-inch. That was convenient because it's much easier to polish them on the inside than it is the outside, but we've done both, as our video showed previously. And so what we wanted to do was go back and look at what were the original capacities that would have been calculated for these windows and their corresponding design loads. And so in this case, on the far left, we see the design wind loads that we had to resist. You see those vary between the units and their sizes, probably due to their location on the building. And so we, to calculate the original design capacity, we went ahead and used the current basic method, although when this building was designed and constructed, it would have been under a preceding version of E1300 to calculate those capacities, but that's now known as the basic method in comparison to the analytical method that we're going to look at. So the question is, how do we adjust our design our capacity in our post-polish state? And what we find is that the basic method does not lend itself to doing this. Okay, it's just not possible to do that. And so fortunately, since we have this new analytical method, we can then do that. So what we did is, to make sure that we're comparing our apples to apples, we recalculated the design capacity of our units with the analytical method, and we notice that there is a significant increase in that capacity, well beyond our design wind loads. And I don't want to go into a whole lot of detail with that, but recognize that that increase, or that proportional increase, is specific to this construction and may not be typical for other constructions or other dimensions of windows. So this just applies to this one. So we use that reduced thickness and reduced RCSS to recalculate the design capacity after after polishing, and we find that we had a relatively small decrease in strength in this case, and wound up being about a 3% reduction. And in this case, that reduction was principally due to the change in thickness, because the light that was controlling these designs was actually the exterior light was controlling the strength. And again, this 3% reduction shouldn't be considered representative of a general case. It is specific to this one. That variation can change depending on the construction and the level of polishing that we had. So I want to kind of go through some of the details and the project outcomes that we had in our case study. So in summary, we ID'd a series of interior lights. Again, they were insulating glass units with blemishes that went beyond the C1036 allowable limits that Mark talked about previously. And of those, many of these were highly customized units, including over 50 different frit patterns across those. And we came up with a total of about 450 units that we restored. And we used we brought in an out-of-town specialist to do that polishing, because we had worked with that individual previously, and we knew that that company knew what they were doing and would do it within what we were expecting. It's not to say that you might not find people locally, but in this case, we went with somebody we knew worked. So what was our cost savings here? Well, what we ended up was the average cost per unit wound up being about $1,500. If we take out having this guy staying in a hotel and eating, that would be about $1,100 on average per unit. And even with that cost, the repair versus replacement savings was somewhere in the ballpark between 5 and 10 times, recognizing that some units have more or less polishing on them, and some units are more or less expensive depending on what they were. So with that, I'd like to turn the presentation back over to Mark, who's going to discuss spontaneous glass breakage.
Thank you, Stephen. And we'll take a look at some nice looking images of nickel sulfide breakage here. This one was taken at nighttime on a project in Beijing with a lot of nice colors in the background. You might try to get this artistic effect on some glass furniture if you're looking for it. But if you're not looking for it and it's your building and it's your glass, and you can see in this photo, it's the exterior light and it can fall from significant heights, that becomes a concern rather than an artistic effect. And just to let you know, the reason we're talking about this is from our perspective, as well as some other glass consultants that we communicate with. The industry is experiencing a resurgence in nickel sulfide induced glass breakage for some reason that is debatable and yet to be quantified. But let's take a look at what spontaneous glass breakage is, a little primer here. It only occurs in tempered glass, typically. Theoretically, it can occur in heat-strengthened glass, though that is very, very uncommon. So it's not a concern for other types of glass. And it is caused by a contamination of nickel sulfide. It's not something that occurs naturally or inherently in any type of glass product or quality of glass. It's not like the strength reducing effects of glass weathering, for example, that are considered in design. So there can be some much less common types of inclusions that lead to breakage that we've seen, but they're even more rare, and those can include silicon and iron phosphide in our experience. The glass, when it breaks, typically breaks into some dice-sized fragments that can readily evacuate the opening. This phenomena diminishes over time. There's a variety of published guesstimates really on how long it takes for it to subside. And the usual time frame is about 8 to 10 years following installation, though exceptions obviously do occur. And currently, there's no reliable or efficient techniques for detecting these contaminations either in the plant, in the float plant, or on the side of the building. So you can't reasonably predict when and where future glass breakage will occur. However, with a significant database of past breaks, you can use some distributions, for instance, a Weibull or log normal distribution, to try to predict the magnitude of future glass breaks. Let's take a look at the mechanism of what occurs in a spontaneous glass failure. And I should point out that the spontaneous breakage is sort of the industry moniker or term for nickel sulfide induced glass breakage. You could probably say a lot of glass breakage is spontaneous, but specifically we're using the term as the industry would define it. Now, as Stephen mentioned before, in tempered glass, heat-treated glass, there's this outer compression zone and intertension zone. The outer compression zones comprise about 20% of the glass thickness at the surface. The tension zones, like the center, 60% or so. And this nickel sulfide inclusion here, shown greatly exaggerated in size, exists in a couple of states. There's what's termed the smaller high temperature alpha form, and then there's the larger low temperature beta form. When the glass is quenched to create these surface compressions and tension zones, it essentially locks the nickel sulfide inclusion into its smaller high temperature alpha form. And then when it's put up on the side of the building, it can subsequently expand. And if it's located in the central 60% of the glass thickness in the tension zone, it can propagate a failure. Now, the start of this phenomena can take months or a year or so, depending on the location, type, and size of the inclusion, as well as exposure conditions. Now, you might wonder what mitigation techniques there are to avoid this phenomenon. There's one in the fabrication process specifically, and it's called heat soak testing. It's largely defined by a European standard that practically everybody uses worldwide. It involves reheating the glass to about 550 degrees Fahrenheit because cumulative exposure to heat will catalyze the transformation of the nickel sulfide inclusion from its alpha to its beta form, causing it to expand, resulting in breakage in the heat soak chamber rather than on the side of the building. Now, there are some that have expressed concerns about the heat soak testing process and that it may relax the beneficial RCSS, or residual compressive surface stress, at the glass surface. However, recent research has indicated that using the typical European process should probably only result in about a few percent reduction of the glass surface stress, relatively insignificant. Should also point out that this heat soak testing, which is been debated here in the US, is ubiquitous in Europe. It's used on virtually all tempered glass that's on the side of a building, especially when it's on the outside of a building when it can fall from significant heights. Let's take a quick look at some misconceptions that exist regarding nickel sulfide as well as heat soak testing. The first would be that there's acceptable limits. And some people have suggested that 8 breaks per 1,000 is the acceptable limit. And that's just a misrepresentation of what Stephen pointed out earlier. 8 breaks in 1,000 is an acceptable breakage rate for glass upon first application of its design load. So that would be typically a uniform wind load. Has nothing to do with nickel sulfide inclusions. Secondly, some have suggested that acceptable rate is 3 or 5 breaks per 1,000 lights. And that represents various manufacturers' warranties for their heat soak tested glass. So in other words, if they have breakage exceeding 3 or 5 lights per 1,000 lights, they'll start replacing the glass free of charge. But it's not an indication of what an acceptable limit is. Then there's this, what appears to be an extraordinarily high average incidence of breakage reported in European literature of 1 break for 4 metric tons. And that's a longer discussion as to how that number came about. But suffice it to say that any average rate that you see or read about, you should interpret with caution, because this is a pretty rare phenomena. So there's many buildings that have 0% of nickel sulfide breakage on the building. So if you have a building, unfortunately, that is experiencing nickel sulfide, invariably you'll experience breakage at a rate much higher than any average rate. And then the last misconception is that heat soak testing is not that effective. You can see by misinterpreting those acceptable limits up above that people have indicated, and manufacturers even have this as on their published literature on the web, that it effectively reduces the breakage rate by 2 to 3 times. And they're misusing the 8 breaks per 1,000 and the 3 and 5 breaks per 1,000 to indicate that reduction. The fact of the matter is that nickel sulfide or heat soak testing has been shown to convert about 99% of all deleterious inclusions. So in other words, the estimated reduction in breakage rate is about 100 times. And also, more significant published research on heat soak testing has shown that the process virtually eliminates any concern about spontaneous glass breakage, and that's 2018 research. So I'd like to wrap things up here and leave you with a few takeaways from our discussion today about your glass sets. First of all, they're expensive and costly, as we've seen. Secondly, if there is bona fide damage, polishing can be a very cost-effective and structurally adequate alternative to just replacing the glass. And lastly, in regards to nickel sulfide breakage, heat soak testing is a very effective mitigation technique for spontaneous glass breakage. So with that, I would like to turn it over to Liz, who will moderate the questions that have been coming in.
All right, thank you, Mark. We will turn to questions now. As a reminder, if you do have a question, please type it into the Q&A box and hit send. And we will try to get to as many questions as possible before the end of the hour. But if we don't get to your question during this call, Mark or Stephen will follow up with you afterwards. So the first question we're going to take is $1,500 per window for polishing seems like a lot, especially for small and less expensive window replacements. Is it always that much?
So the answer to that question is no. For example, if we have a smaller window with a single 12-inch diameter repair area, the cost could be quite a bit less, maybe on the neighborhood of a couple of $100s. So it depends on the level of damage and how easy it is to get to it.
Okay, we'll take our next question. Does the polishing process used to remove scratches leave visual distortions?
So the idea is to do the polishing to where you have minimal noticeable distortion. This is going to be a function of the depth of the blemish. If it gets a little bit deeper, then you can actually create a lens effect. And so we did a few of those that we thought probably needed to be replaced, but we wanted to see if we could repair them. But we had one where it wound up making a noticeable difference, and so they were going to have to replace that one anyway.
Is nickel sulfide inclusion and associated breakage more common in imported glass?
This is Mark. I would say that based on an unofficial review and recollection of all the nickel sulfide glass breakage projects we've done, is that it does affect both domestic as well as internationally sourced glass.
Okay, next question. If you perform the polishing on the interior of the pane to remove a blemish, does that affect the strength rating of the glass from the outside?
Okay, so this is Steve. I want to kind of pick that apart. If we have an IG unit and we polish the interior light, we haven't actually done anything to the exterior light. On our example, we noticed a slight reduction in that one, and that was, and so we're taking kind of the weakest, the kind of the weakest link chain, if you will, or the weakest link in a chain approach when we do strength of glass. And so we were not really reducing it, but the effective load resistance of the entire unit can be reduced since we're taking that interior light with the reduced thickness and reduced RCSS.
Okay, next question. Curtain wall contractors generally push back on replacement of spontaneous breakage if it's, quote, within manufacturer's acceptable breakage rate. How can an owner argue against this if there is not breakage rates for nickel sulfide inclusion?
That's a great question. And because it's a contamination, we have been involved on projects where the argument is made that it's a contamination and it's not inherent in the quality of glass that was specified and purchased. So there does not need to be an acceptable rate because the expected breakage from nickel sulfide should be 0.
Okay, we'll take our next question. Can you polish glass with frit on it?
I'll answer that one. The short answer is depends. If the blemish is on the fritted surface, then the answer would be no, or not easily, because we'd be removing part of the fritted surface as well. However, if it's on the side of the glass that doesn't have frit on it, then yes, we can polish that just fine.
Okay, next question. Is there ever a case when you should just replace the glass rather than polishing it?
Well, let's see. The more individual polishing areas as we saw in the videos that you have on a individual glass light, the more likely it is that the polished glass may have some distortion, objectionable distortion when you're done with it. So I would say it varies from project to project, but on one past project that comes to mind, we set a maximum number of polished areas at 10. And that's where we drew the line between something that was viable in terms of polishing versus something that needed to be replaced.
Okay, we have time for one more question. Okay. Do heat strengthened glass with nickel sulfide inclusions break in the same pattern?
I can take that one. Maybe Stephen will chime in as well.
Sure.
But the probability, especially with the limits now set in ASTM C1048 for heat strengthened glass to have large enough nickel sulfide inclusions within the tension zone that has lower stresses than tempered glass to cause breakage is very small. But where we've seen it occur in glass that was just slightly higher residual compressive surface stress than allowed by ASTM C1048, the nickel sulfide inclusions broke the glass into larger fragments than you would typically see in tempered glass.
Stephen, did you want to add anything to that?
No, I think Mark covered it well. And so the short answer is we expect heat strengthened glass to break more like annealed glass versus the small dicing, if you will, effect that we get with fully tempered glass.
Okay, so that is all the time that we have for questions on the live call today. One more reminder that we will follow up with you afterwards to answer your questions if we didn't get to them on the call. We'd really like to thank you for joining us, and we hope it's been educational. Thank you, Mark and Stephen, for your presentation. As a reminder, you will receive an email after today's webinar that will include instructions on how to request credit for participating in today's webinar. And that follow-up email will also include a recording of the webinar for you to share with colleagues. So again, thank you for your time, and we hope you have a great rest of the day.